everyone, and thanks for watching Edupedia World videos. From this video we begin our study of the atomic particles and we start with electrons. Now the discovery of electrons historically comes from one simple experiment, and in that experiment we have what is called a discharge tube. That is a tube which has two sides attached to two terminals and is filled with gas. So if you take a battery, this is supposed to be a very high voltage battery, and the setup you can do is you can have a tube that is completely filled with the gas, and there are two terminals inside the discharge tube. So this will be the negatively charged terminal, this will be the positively charged terminal, and this discharge tube is filled with the gas. This terminal is called the cathode, this is called the anode, and this whole setup is called the discharge tube. Now what we observed in this experiment was that if this voltage was high enough, then this circuit was completed and there was actually current going through. Current goes from this direction and comes out from this direction. Now that is not really supposed to happen because gases are generally not good conductors of electricity and there is no wire connecting this terminal to this terminal. But at sufficiently high voltage we do see a current, and you could measure that current with an ammeter if you wanted to keep one here. So the explanation of that was, with a high enough voltage, some particles from the molecules or atoms of the gas get loose, and those particles conduct electricity. Those particles are what we now call electrons. So when there's a high potential, this gas becomes ionized and its atoms break up into positive ions and electrons, and the electrons are fast moving particles, so they immediately move in this direction and they are attracted by the positive potential, so that helps as well, and that creates a current in the opposite direction. So when this experiment was first done, we could put some material inside this discharge tube which would help us to see the particles actually moving. When the particles moved, they left an impression and we could see where the particles were moving. And we saw a stream of particles coming from the cathode towards the anode, and that stream of particles was called cathode rays. Cathode rays are nothing but rays coming from the cathode, and now we recognize cathode rays to be just a stream of fast moving electrons. So there are some properties of cathode rays which you need to know. The first property is they are emitted normally from the cathode. So if in the discharge tube, instead of a flat cathode, if you had a cathode like this, then electrons would be focused at a particular point. You could do that. So electrons are always emitted normally from the cathode. Second is they travel in straight lines. You can test this by putting some object in front of the cathode rays. These would be the rays going, and if you put some object here, then there would be a shadow on this wall, meaning that the cathode rays would not be reaching the points beyond this opaque surface. The third is, and all these properties initially were puzzling to scientists, but now all of them can be easily explained by assuming cathode rays are just a stream of fast moving electrons. So the third one is they exert mechanical force on the objects they strike. This basically is a way of saying that cathode rays have momentum. Fourth, they produce heat when they strike a metal surface. This is another way of saying cathode rays have their own intrinsic energy. And also, probably most importantly, they are deflected by electric and magnetic fields. or by electromagnetic fields. Now this last one is important because it tells us that cathode rays have a particular charge, because only charged particles are affected by electric fields or magnetic fields. So this tells us that the stream of particles which constitute cathode rays are not electrically neutral, and in fact you could actually look at the direction in which they deflect. For example, if this is the cathode and you are able to see electrons reaching this point, being emitted straight and reaching this point, then if you take a positively charged particle here, then these electrons will be attracted and this point will shift to this point, because the steam instead of going straight will be deflected towards the positive charge. If instead you take a negative charge here, the stream will go upwards because it will be repelled and you'll actually see the shadow here. So not only are they deflected by electric and magnetic fields, they are deflected in the same direction that a stream of negatively charged particles would be deflected. So this tells us that these particles which constitute cathode rays are negatively charged. Now all of this can easily be explained by assuming that there are small particles negatively charged which are called electrons, and cathode rays are basically a stream of fast moving electrons. So the next step was to identify the properties of an electron, the charge and the mass of an electron. There was also the puzzle of why they are negatively charged, why don't the positively charged particles move, but that's the subject of discussion for the next video, in which we actually discuss the nucleus as well. Right now we are focused on the electron. So the next step was to measure properties like the charge and mass. However, because of experimental constraints, it was a long time before the charge and mass were individually discovered. What was easily discovered before that was the specific charge of the electron. And specific charge is nothing but E by m, or the ratio of the charge and the mass of the electron. So this was discovered quite easily by a simple experiment, and that experiment consisted of a discharge tube in which you had this was at a negative potential, this was at a positive potential, and you had a stream of cathode rays, and this went and touched the appropriate point directly opposite it. Then you applied an electric field in the downward direction. The electric field in the downward direction caused the electrons to move slightly upwards. And then what you did was you added another magnetic field such that the force due to that magnetic field on these charged particles would be downwards. This electric field would cause an upward force that would be equal to EE, and the magnetic field was so arranged that it would cause a downward force which would be equal to E times VB. Right, we've done this all before in electromagnetism. And then the fields were so arranged such that the stream of particles went away undeflected. So in that case, the electric and magnetic forces were exactly opposite to each other, and the relation we would have gotten was EE is equal to EVB, or V is equal to E by B. Now the next step was, we already knew the voltage by which this battery was attached, so we knew the potential difference between these 2 points. Now, assuming that they started from rest here, which is a reasonable assumption, by the time these electrons reached this point, they had a kinetic energy half mv squared is equal to ev, because v is the potential difference through which they are accelerated. Now you take these two equations and you simplify them, and what you'll get is E by m is equal to E square by 2b squared v. E and b are arranged by us. We keep changing them until there is no deflection, so we can easily measure E and B, and V already we know because that is the voltage of the battery. So using these three knowns, we were very easily able to measure the charge by mass ratio of the electron, or the specific charge of the electron. Now it was quite a while later that a scientist, Robert Millikan, devised an experiment through which he was able to measure just the charge of the electron, and of course if we have E by m and if we have E, then we'll be able to measure m as well. And that experiment is called Millikens oil drop experiment, and it is one of the most important and widely known experiments in all of physics. In this experiment, you had an ionized gas which had a lot of free electrons moving, and you sprayed some oil through that. So you had some oil drops, that's why it's called the oil drop experiment, and those oil drops, due to friction, got some electrons attached to them and hence got a negative charge. And the oil drops were easy to observe through a microscope. So then what happened was, this was the, let's say, the setup, a cylinder in which there might be a hole here, and you spray oil into this hole, and so it goes inside this cylinder and it forms oil drops, which then due to friction get electrons attached to them and become negatively charged. Then there was an electric field in the downward direction, let's call it E. So that electric field resulted in a force in the upward direction due to the electron. We already knew the electron was negatively charged. Now the task was to measure the charge of the electron. So the force on the electron due to this electric field would be upwards, and this electric field was adjusted such that the oil drops and the electrons attached to them became completely stationary. So if they were completely stationary, then the viscous force acting on them was zero, because we've seen in fluid dynamics that viscous force is proportional to the velocity, or the velocity gradient. So in that case, the free body diagram would have been, this was the electron, and there would have been a force QE upwards, and there would have been a force of buoyancy upwards due to the air, and mg would have been downwards. And since we keep adjusting E until this is at rest, the equation was QE plus B is equal to mg. Now you can write B as, if you assume the radius of the oil drop to be r, 4 by 3 pi r cube times rho of air, and m you can write as 4 by 3 pi r cube times rho of oil. So you put these here, and I'll not spend time simplifying it. The result you get is Q is equal to 4 pi r cube by 3e rho minus sigma times g. Now this would be well and good, except it is very difficult to measure r. We can easily measure rho, sigma, g and e, but to measure the radius of an oil drop is quite difficult. So we had to do something different to specifically measure the radius of the same oil drops. So what they did then was, they switched off the electric field, and they just waited. If you switch off the electric field, it will start moving downwards, and they just waited until terminal velocity was reached. Terminal velocity means the velocity is constant and the frictional force exactly opposes the gravitational force, so there is no net acceleration. In that case, the viscous force upwards would have been 6 pi eta rv by Stokes' law. We've done this before as well, and the equation would be mg is equal to 6 pi eta rv plus b. Now again, b we can write as this, and the only unknown is r, because we can measure mg, pi and eta, and m we can measure because of rho of oil. And if you take r from this equation and you put it into this equation, then the final result you get is, and I would hope that you can try this at home yourself, you should try this at home, the final result was q is equal to 18 pi by e square root of eta cube v cube by 2 times rho minus sigma g. Often we neglected sigma in front of rho. You can do that in questions if sigma is not given, because then the density of air is actually much smaller than the density of oil. But for the sake of completeness, we take this, and so in this every quantity can be measured. Eta we already know, v can be measured by looking at how much distance it falls through and how much time, and with this equation we can actually measure the charge on those oil drops. And the interesting thing was, whenever we measured the charge on those oil drops, it was never the same, but it was always a multiple of a particular quantity, and the quantity was 1.6 into 10 to the power minus 19 coulomb. So sometimes the charge on the electron, let's call this E, this is the charge on the electron. So sometimes this Q measured would be equal to E, sometimes it would be equal to 3E, sometimes it would be equal to 4E, but it was never equal to half of E or a third of E or 5 by 7 times E. And that told us that an integral number of electrons were attached, and if the charge was 3e, then that meant that 3 electrons were attached to the oil drop. The lowest possible charge always was 1.6 into 10 to the power minus 19 coulomb, and that is how Robert Millikan was able to measure the charge on the electron. And because we already knew the specific charge, we were able to measure the mass of the electron as well. Then came the question of why do we have negatively charged particles which are moving even though every body as a whole is electrically neutral? And for that we needed to answer what the structure of an atom as a whole was, and that's the topic for the next video. Thank you.